In this lesson, we will be solving trig equations for specific values. In previous lessons, we were verifying trig identities which are true for all values of the angle. In today's lesson, we will be looking for a specific angle that satisfies the equation. If you look at the first example here, it says solve sine of theta is equal to 1/2. So we are looking for specific angles, specific theta values that give us an output of 1/2. Right above it here we have the graph of sine, and if we look at the output, the height of the graph, we are looking where it would be equal to 1/2. That happens here at pi over 6 and here at 5 pi over 6. We also can verify this using the unit circle. So everything that we're going to work on today is going to reference this unit circle. So just to refresh, if we are looking for values on the unit circle, the sine is always equal to the y-coordinate divided by r. Recall that on the unit circle the r value is equal to 1, so essentially sine is just the y-coordinate. For cosine of theta, it would be x over r. Again, r is 1, so cosine is just the x-coordinate. Tangent is y over x. Cosecant, the reciprocal of sine, would be r over y, and again r is 1, so it will be 1 over y. Secant is 1 over cosine, or 1 over x, and cotangent is x over y. So we'll be using those ratios in conjunction with the unit circle to find our answers for these problems. If we look at this equation, sine theta is equal to 1/2. If we want to verify the answers with the unit circle, we would be looking where the y-coordinate is equal to 1/2. So the y-coordinate has a value of 1/2 here in the first quadrant, here in the second quadrant, here in the third, and right there in the fourth quadrant. We do need to be very careful with the positive and negative signs. The problem asks just for 1/2, so a positive 1/2, which means two of these answers in the second and third quadrant, don't work. They give us, third and fourth quadrant, they give us negative 1/2 in the third and fourth quadrant. So we actually don't want those two values. We have this angle here in the first quadrant gives us positive 1/2 as the y-coordinate, and again here in the third quadrant with a y-coordinate of positive 1/2. So those are the two solutions we're looking for. The solutions here, like I showed on the graph, are pi over 6 and 5 pi over 6. So it's much better to look at the unit circle to use that to find these than to try to get it off of a graph. And we don't want to use a calculator on these. We don't need to use a calculator on any of these. We can do it all from the unit circle. Just a few things to note. I know that the book has different ranges for their values. They can ask for all solutions. We're going to do it over the interval 0 to 2 pi. So we can always assume that we're looking for answers over 0 to 2 pi. Just to keep things consistent, to keep things routine for us, it'll always be from 0 to 2 pi. Right, in the first real example here where we need to do work, we're going to do algebra to isolate the trig function. So what we want to do is get all of the numbers to the right side in this case and the trig function to the left. That's going to be the general format for these: trig on the left, number on the right, but whatever you're comfortable with, as long as you keep the positive and negative signs straight, you should be good to go. We're going to move this one. I'm going to move this tangent to the left and move this square root of 3 to the right. So we want to do that with our basic algebra, so we are going to subtract tangent of x from both sides and add the square root of 3. So when I subtract 2 tangent minus tangent, I get 1 tangent here on the left-hand side. Those square roots of 3 reduce, tangent reduces, and we have the square root of 3 on the right side. So at this point we now have a trig function is equal to a value, which is what we're looking for. Once we get to this stage, we can go to the unit circle and try to find that value as a coordinate on the unit circle. If we go to the unit circle though, None of these coordinates are the square root of 3. Tangent is a quotient, so we are going to need to do some division to figure out which of these angles produces a value of square root of 3. If you don't know off the top of your head, we do want to go ahead and try the 3 possible combinations to see which would give us the square root of 3. We don't want to use the quadrantal angles because we can be dividing by 0. That's not going to be the right answer. So we have pi over 6, which would be 1/2 for the y coordinate, over square root of 3 over 2 for the x coordinate. The middle angle there, we have the square root of 2 over 2 for the y coordinate and for the x coordinate. And the third possibility here at pi over 3, we have a y coordinate of square root of 3 over 2 and an x coordinate of 1/2. So those are the 3 possibilities. One of those should produce the square root of 3. So there's several different ways we can go through simplifying these. This first one, we have 1/2 over the square root of 3 over 2. I'm going to go ahead and multiply by the reciprocal of the denominator. These 2's can cancel out, and we are left with 1 over square root of 3. That is not the square root of 3. We can rationalize this just to be sure by multiplying top and bottom by the square root of 3, and we end up with square root of 3 over 3, which is not what we're looking for. So that is not the solution. In the middle here, in the red, we have the square root of 2 over the square root of 2 over 2. So we have the same thing top and bottom. So really all of that reduces, and we are left with 1, which is not the answer we're looking for. So hopefully this in the green is the correct solution. For this one, again, we can multiply by the reciprocal of the denominator, and again the 2's reduce, and we are left with the square root of 3 over 1, which is exactly what we need. So this is the solution that we are looking for. So if we go back over to the unit circle, when the y coordinate was square root of 3 over 2, the one circled in green there is pi over 3. So this is a solution. If we look around the unit circle, there are other places where those same values occur for the x and y. In quadrant 2, it's right there, it's 2 pi over 3. In the third quadrant, it's at 4 pi over 3 and 5 pi over 3 in the fourth quadrant. Not all of those are necessarily the answers that we need. If they are the wrong positive or negative sign, we can't use them. So if we look in the second quadrant, the tangent is negative since it's a positive divided by a negative. So we don't want that answer. That does not work for us because we're only looking where tangent is positive, square root of 3. In the third quadrant, since they are both negatives, tangent is again positive, so this solution does work. So we do have answers at pi over 3, 4 pi over 3, and the last value that we could have is 5 pi over 3, but since the y is negative and the x is positive, the tangent is now negative again, so this does not work. So the 2 solutions that did work are pi over 3 and 4 pi over 3. The next example here with sine is a very similar process. Please give that a try. At this point, pause the video and work through the example with sine. Let's take a look at the solution here for this equation for sine is equal to 2 sine plus the square root of 2. So we want to start out doing something similar we did in the previous example. We want to move the trig functions so they are all on the same side. We're going to do that again with subtraction. So 4 sine minus 2 sine, we're left with 2 sine of x on the left side equals square root of 2. The next step would be divide by 2. We have sine x equals square root 2 over 2. We are always able to subtract the trig functions. We're never allowed to divide the trig functions. We're allowed to divide the constants, but we are never allowed to divide the trig functions. So we get sine is equal to square root of 2 over 2. Again, sine from our chart earlier is the y-coordinate, so we're looking onto our unit circle for a y-coordinate that is positive square root of 2 over 2. So a y-coordinate of square root of 2 over 2 happens there at pi over 4, there at 3 pi over 4, there at 5 pi over 4, and again, one last time at 7 pi over 4. 5 pi over 4, though, and 7 pi over 4, they are negative square root of 2 over 2. So even though they have the right numbers, they are the wrong positive or negative sign, so we can't use them. Just like the previous example, we get two solutions. So the two solutions happen at first angle pi over 4 and again at 3 pi over 4. We had to throw away 5 pi over 4 and 7 pi over 4 because they were negative coordinates. The cosine example here, 5 cosine of x, this is very, very similar to the sine problem. So if you want to try another problem, please pause the video again and work on the cosine problem. So this problem has basically the same steps as the sine problem that we just did. The first would be to subtract the trig function to the left-hand side. 5 minus 3 is 2 cosine. And then to divide by that coefficient, dividing by 2. So we have cosine of x equals the square root of 3 over 2. The exact same steps that we just did with the sine problem. Different coordinate that we need to find, we're looking for square root of 2 this time, and different trig function we have cosine, which from our table, our chart, is the x coordinate. So we are looking for the x coordinate to be positive square root of 3 over 2. So the x coordinate is positive square root of 3 over 2. That occurs for the first time here at pi over 6, so that works. We do have a square root of 3 over 2 here in the second quadrant, but it's negative, so that is not a solution that we want. Same thing with this down here, it's negative, so we can't use that. So our second solution comes from 11 pi over 6. So the two solutions that work for us that are positive are pi over 6 and 11 pi over 6. The three examples we've done so far, we have two solutions for each of them. The next two examples that we're going to see are slightly different. We'll notice there are now squares in the problems, and there are no trig functions on the right side. So we are not going to be subtracting to get the trig function by itself. We need to eventually take a square root to get to our answer. And when we do that square root, it's going to produce us more answers than the previous examples. The idea is still the same. We want to get the trig function by itself on the left-hand side, and we want to use our algebra to do that, so we're going to start by subtracting 1 from both sides. So we have 4 sine squared is equal to 3. Again, same second step as the previous two problems. We are going to divide by that coefficient. Those reduce. We have sine squared equals 3 over 4. This is when we need to take the square root. So we take the square root of both sides. And when we do that, we have sine, which is what we want on the left-hand side. Then we have the square root of 3 over 4. It's very, very important that we remember to include the positive and negative sign when we are taking this square root, because we have the possibility now to have the positive coordinate and the negative coordinate. We are going to have more answers for these squared problems than the previous examples. So we have sine of x is equal to plus or minus the square root of 3/4. Well, the square root of 3/4 is not on the unit circle. So we do need to kind of clean that up just a tiny bit here before we go to the unit circle. So we still have plus or minus. The square root of 3, we can't do anything with that, but the square root of 4, the denominator, becomes 2. And now the square root of 3 over 2 is a value we can find on the unit circle. Again, we're working with sine, which is the y-coordinate. So now we're looking for the y-coordinate to be square root of 3 over 2. And it does not matter if it's positive or negative. So we should see it 4 times. So in the first quadrant, it happens here, square root of 3 over 2. Second quadrant here, square root of 3 over 2. Third quadrant here, it's negative square root of 3 over 2, but we are allowed to have negatives now that we did a square root. And finally, in the fourth quadrant, we see negative square root of 3 over 2. So all 4 of the quadrants produce an answer for us. We have 4 solutions this time at the pi over 3 angles. So our answers are pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. So when we are working with these square problems, we do have more solutions than the previous problems where it was just addition, subtraction, multiplication. The next example there with the cotangent will happen with roughly the same algebra. We do have cotangent, which is a quotient function now. So you do need to look at the coordinates as a quotient to get your solution, but the work is a little bit easier than the tangent example we did at the start. So please pause the video at this point and work through this example. So the work here is similar to the sine problem that we just did. We want to start by subtracting the constant there on the end. On the left, we still have our trig function, 3 cotangent squared. And on the right, 7 minus 4 gives us 3. When we do our division, we're going to get a much easier coordinate to find than the previous tangent example. So we are looking at a 1 when we take the square root of both sides. The square root of 1 is still 1. We just need to remember that we have plus or minus with the square root. So plus or minus 1 is what we're looking for. So if we kind of reference the problem we did with tangent earlier, we got 1 when the x and y coordinate were the same. So what we're looking for is the place on the unit circle where the x and y coordinates are the same. It doesn't matter what is positive and negative, we just want the same values. So that's going to happen at all of the pi over 4 or 45-degree angles, where we have the square root of 2 over 2 and the square root of 2 over 2. We are writing all of these in the radians with the pi fractions, so don't go back to degrees, stay in radians. But those are the angles that we're looking for. We have, again, 4 solutions, just like with the sine problem there. Pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. So we have 4 solutions. Since the trig function was squared, we have both the positive and negative versions of the coordinates. The last example here is to solve by factoring. So if we look at this equation, it's very tempting to start by dividing by cosine. There are cosines on both sides. Theoretically, that could work, but it does not. There are 2 reasons here why that's not going to work for us. Just like the verifying identities, when we weren't allowed to work across the equal sign with division, it's because there's a potential to divide by 0. Cosine does equal 0 twice on this interval from 0 to 2 pi. So if we divide by cosine, we can divide by 0, which is not allowed. So that's the first and foremost reason why we don't want to do that. Second is, let's say we did and we reduce those out, we would have sine x is equal to 3. Sine x is never equal to 3. 3 is not a unit circle value. There is no 3 hanging out by itself anywhere on the unit circle. So that doesn't work. That's not a solution. There's nothing that works out of this problem. So if we just throw away the cosine, if we divide it from both sides, we actually make this problem unsolvable. And that's not the case. There actually are solutions to this problem. So we don't want to start by dividing. Dividing the trig function is never an option. So in order to solve this, in order to be able to factor it, we need to do the same process that we did when we solved other things by factoring, i.e. quadratics. So we want to get all of our terms to the left side and get a 0 on the right. And you can do it the other way around, but I like getting the quantities to the left and a 0 on the right. So we're going to do that with subtraction. We're going to move this 3 cosine to the left side. And then the right side is now equal to 0. So by doing that, now we have a constant or a common term, on the left side between both of those pieces. So the cosine can be factored out. So this is very similar, again, to what we saw with quadratics, something like this. X squared minus 3x is equal to 0. In order to solve that, we can pull an x out of both of these. We're left with x minus 3. And then to finish solving that, we'd take each of those pieces and set it individually equal to 0. So x would be 0 or x would be 3. We're going to do the exact same process here with these trig functions. So cosine is the common term. That is what we're going to factor out. So we pull the cosine in front, and then inside the parenthesis goes the sine and the negative 3. So we have pulled out the common term cosine. We are left with sine minus 3 as the other factor, and that is all equal to 0. Just like the quadratic example I've got over to the side, we want to take each of these pieces and individually set them equal to 0. So either cosine x is equal to 0 or sine x minus 3 is equal to 0. So there's no work to do, no algebra work to do. We can go look for that on the unit circle. Again, cosine is the x-coordinate from our little table up there, so we're looking for the x-coordinate to be 0. So the x-coordinate equal to 0, that happens twice at the quadrantal angles of pi over 2, happens right there, and 3 pi over 2. So cosine of x is 0 at pi over 2 and 3 pi over 2. On the other piece, we have sine minus 3 is equal to 0, so we want to go back to what we were doing before, where we get the trig function by itself and the number on the right. So we have sine of x is equal to 3. Talked about at the beginning of this example, sine can never equal 3. 3 is not a unit circle value. Sine is always in between -1 and 1. So for this portion, there is no solution. We don't have anything that works in that for x. And that can happen. We can have parts that have no solution, but overall this equation does have solutions. It has 2 solutions, and those solutions come from the cosine part equaling 0. So those 2 solutions are pi over 2 and 3 pi over 2. Given different circumstances, we could actually find some other solutions for the other part. Say the coefficient was 1, and we had sine is equal to 1, then we can actually find more solutions that would work for this problem. But with the specific values we were given in this problem, the sine portion that we factored apart doesn't produce any additional answers. So the only answers, again, come from right there. So there is homework that goes with this. We have 5 to 15 odd here, and this is only the first part of the section here on solving. So we're going to look at some other methods of solving these equations in the next set of notes, but for now it's just basic algebra. And remember, all of your answers need to be taken from the unit circle. There should be no calculator work involved on this. So please reference the unit circle in the notes here and work through the examples, take a look at the homework, and we'll go over everything next class.